All right, the next topic we're going to review is precision and accuracy. Precision and accuracy we will use a lot in labs this year to kind of interpret our data. Was it accurate in terms of close to a target value? That would be representing the middle of the dartboards. Or was it precise? Was your data consistent? If you have repeated trials, were you getting relatively the same values for your trials? So the bottom right-hand corner is representing both high accuracy and precision. The top left-hand corner is representing very little accuracy or precision because the targets are all spread throughout the dartboard and they are not close to one another or to the center. You often, well, you don't often, but you definitely can have low accuracy that have high precision. Let's say if there was a measuring device that was off, you might be getting really consistent results, but you wouldn't necessarily be getting accurate data. And then you can also, when you do repeated trials, have some values that are right on the target and some that are a little off. So they're not super precise. They're definitely more precise than they were in the top left corner. But in the bottom left corner, you can kind of see that there is definitely a little bit more movement between the individual measurements, which makes that have less precision. But on the whole, they are fairly accurate compared to what they were trying to reach. So as I just talked about, accuracy is the comparison between an experimental value to a known or true value, an accepted value. Percent error is an equation you have seen before, and it is one you want to make sure you know you're going to be using it fairly often. It will never be negative because it's always the absolute value, the difference between the two values you're comparing over your accepted value. You always want to compare it to the known value, the true value. And your percentages, I'm always going to let you round those off to one decimal place. So we're not going to have to worry about sig figs with those. I don't want you to stress out about that. Precision is how close your measurements are to one another. In the past, we've used range to kind of look at that to examine how close they are. You can also talk about precision in terms of decimal places. The more information that's able to be provided by a measurement, the more precise it's able to be. And so there are also calculations that can be done called deviation, average deviation, absolute deviation, percent deviation. But range is kind of a quick and dirty dodge as to how precise, how reproducible your results are. If you're able to get consistent data over and over and over again, well then how you're conducting your experiment most likely is being done well. It might be that if you aren't accurate, that you're not reading the device properly, but you're consistently reading it improperly, or that there's a calibration error with one of the devices you're using to obtain your measurements. So we're going to do one example with precision and accuracy. Mass and volume of water was measured 3 times by a student in lab at 25 degrees Celsius, used to calculate its density. Temperature is kind of important with density. I'm just going to briefly talk about this because temperature can affect the volume. So densities can only be reported for a substance accurately if it's given with a temperature because that can make it vary. So in this particular example, the 3 densities of water measured at 25 degrees Celsius were 0.975, 0.990, and 0.955. And the accepted density of water is actually 0.998 at 25 degrees Celsius. So the first thing we're going to do is calculate an average. Add the 3 values together, divide by 3, the 3 being the experimental values. All 3 of those had 3 decimal places in their measurements, or from their calculated measurements. And you're dividing by 3, which is an exact value. That won't affect its sig figs. So when we report our average, it should also go to 3 decimal places, 0.973 grams per milliliter. The range is the difference between your highest and lowest value. Your highest is 0.990 and your lowest is 0.955. And so that gives me a range of 0.035. All right, and when we compare that 0.035 to our average, it's a very small percentage of that average value. So although you may look at those and go, I'm not so sure those are super precise, they actually are fairly precise based on the data that we have available. We're finally going to use that accepted density of water now to calculate percent error. That's the one we're comparing to 0.9732. So our accepted value gets subtracted away from the experimental value. We divide by that accepted value and then multiply by 100. I told you that you don't have to worry about sig figs so much with percentages as long as you round it to one decimal place. So you do want to subtract first and then divide because of the parentheses, which are basically our absolute value signs. So we take the difference, we divide, and we get a percentage of 2.5. And I'm not sure why the times 100 isn't here. There should be a times 100 here. I'm sorry. Okay. So hopefully this will help you with the precision accuracy section of your summer assignment.